So load deflection behavior of a prestressed concrete beam. Okay. So students, here you can see the graph of the load deflection curve of the prestressed concrete beam. So this is x-axis, this is y-axis. In x-axis is deflection and y-axis is the load. So initially you can see here, we already told initially the beam is bent upward. So if you apply only prestressing force, so you can see the curve is going like this. That means reversely. The curve is going like this. So this curve is called camber, the distance from the 0 point to the extreme bend point, extreme deflection point is called camber. Okay. So this camber is nothing but the upward deflection. So after that, after if you are applying so up to this portion, that means up to this portion, only prestressing force only we are applying. So imagine initially we are applying only prestressing force. So the beam bends upward. Okay. So now after that the beams are placed in the respective place. Now sulfide and live loads are acting. Okay. So if sulfide live loads are acting, what happened? So again the deflection will goes downward. Okay. So you can see here from this starting point, that means in somewhere in the load. So it will goes like this. Okay, it will goes like this. So this type of deflection occurs when live load is acting. Live load is in the sense external load or imposed load is acting on the beam. So this is the point of working load and this is the point of cracking. And this is the ultimate load point. And this is the failure point. This into mark is nothing but the failure. The beam will fail. Okay. So deflection of prestressed beam essentially differ from behavior of reinforced concrete beam. So in case of reinforced concrete beam, there is no camber will not occur because it will directly take sulfide and the live load only. So the deflection will be only downward. Okay. So we can take advantage in using desired camber. The deflection are produced by sulfide, prestress and live loads. Okay. So in uncracked stage, the deflections are computed using classical elastic theory. Okay, uncracked stage. In classical elastic theory, assume that the beams has a homogeneous elastic body. Homogeneous elastic body is nothing but when load is removed means it's regain its original shape. That is called elastic material. Okay. In the estimation of deflection of post-tensioned bonded beams, the gross transformed section is to be used. Okay. So in the gross area, including the steel area, is transformed into equivalent area of concrete. That means transformed section. Okay. So in case of unbonded beams, the net section of the concrete, net area is nothing but gross area minus depth area is to be used. It is to be noted that the reasonable estimation of deflections can be done by using gross moment of area for practical purpose. Also, the change in prestress can be neglected. When the tensile stress developed due to the load exceeds the tensile strength of concrete, cracking occurs. See, we know that every concrete having some tensile strength. Okay, it depends upon the grade of the concrete. If grade of concrete is higher means tensile strength also increases. Okay, so the load deflection behavior is non-linear. So linear means straight, non-linear means curve. Okay, after cracking the load, you can see here in this curve, in this diagram. So up to cracking, it is linear. You can see this portion. It's a straight line. Okay. So after cracking, it is non-linear. So why means due to cracking, the moment of inertia is changes. If crack happens means before that exactly BD is exactly is that. But now the moment of inertia will change. If crack happens means the moment of inertia is changes. So it behaves like a non-linear. Okay. So due to cracking, the flexural stiffness reduces and the moment of inertia drastically decreases. Okay, just now I said. Okay, so this non-linear curvature mainly occurs due to the reduction in the moment of inertia. Okay, the cracked moment of inertia is of in the order of 1/3 to 1/2 that of uncracked section. Suppose BDQ by 12. This is for uncracked section, means cracked section, it is 1/3, only half or 1/3 only. Okay. So in essence, the deflection of the beam increases faster with the increase of cracking. Okay. So once it is cracked, after that, continuously the moment of inertia changes. That means moment of inertia decreases, and also cracking and deflection also keep on increasing. Okay. So this diagram is very, very important, students. The load deflection behavior. So sometimes in the examination they will ask, so elaborate about load deflection curve of the prestressed concrete beam. So you have to draw this diagram and you have to explain this one. Okay, students. So now we will go to the problems. Okay. So computation of deflection of uncracked section. So this is the topic given in your syllabus. So we already know there are two types of deflection. One is short-term deflection and long-term deflection. So short-term deflection is nothing but deflection due to dead load, deflection due to live load, and deflection due to prestressing force. Okay. So these are all called short-term deflection. So you can see here, I mentioned here. But in case of long-term deflection, how to calculate long-term deflection? So in this long-term deflection, we have to add loss ratio and creep coefficient. Okay. So this formula is suggested by Lin. This is a scientist, Lin. Gave the approximate formula to estimate the long-term deflection. That means del L. Del L is nothing but long-term deflection, which is equal to deflection due to loads. Deflection due to loads in the sense deflection due to dead load and live load. Next, deflection due to prestressing force. Okay. Next, PT divided by PA. What is this PT divided by PA? Okay. So PT is nothing but the prestressing force, final prestressing force divided by initial prestressing force. PT is nothing but final prestressing force. PA is nothing but initial prestressing force. And pi is nothing but creep coefficient. Pi is nothing but creep coefficient. Okay. So this is the formula suggested by Lin. Okay. So for deflection due to dead load, live load, prestressing force, we already seen in last class. Okay, student. So for in this topic, that means in this deflection topic, 5th unit, these two formulas are very much important. Only these two formulas: short-term deflection formula, long-term deflection formula. Once you know this formula, we can do any problems in the deflection part. Okay. So now let us see the first problem, first and simple problem. So a simply supported beam of span 9 meters and the cross section 250 mm by 500 mm is prestressed by a single cable with a prestressing force of 200 kN. The cable profile is parabolic with 50 mm below the centroid at midspan and 0 eccentricity at supports. Take EC equal to 35 kN per mm square and the density of concrete is 25 kN per meter cube. Calculate the upward deflection due to prestress at midspan. Okay. So first understand the question. What are the data they given? One is span of the beam, 9 meters, and the cross section. That means beam size 250 into 500. And the prestressing force 200 kN. Okay. So the shape of the cable profile is parabolic. So in this topic, the shape of the cable, profile of the cable is very much important. Okay. So parabolic with 50 mm below, the eccentricity is 50 mm and 0 eccentricity at support. Okay, there is no eccentricity. That means the point of application of prestressing force and the centroid of the beam both are same at support. Okay, but at midspan there will be eccentricity of 50 mm. Okay, next take EC equal to 35 kilonewton per mm square. 35 kilonewton per mm square, and the density of concrete is 25 kilonewton per meter cube. Calculate the upward deflection due to prestress at midspan. Okay, so in this type of problem, they won't give diagram. So diagram and all you have to draw. Okay, so first to draw this cross section and longitudinal section of the beam. You can see here size of the beam and the cable and centroid distance. Okay, sorry, eccentricity E. So this is your E, 50 mm. So this is your longitudinal section. The span of the beam is 9 meters. So here, what is the scheme? Calculate the upward deflection. That means only short-term deflection. So what are the deflection will come? So only prestressing force and self-weight. Okay. So here you can see so students, here you can see what is the formula in case of a parabolic tendon having eccentricity at midspan and 0 eccentricity at support. What is the formula? So the formula is del P is equal to minus 5/48 PEL square divided by EA. Okay. So since they asked only upward deflection, for upward deflection, only prestressing force, only we have to consider, because due to prestressing force only upward deflection is occurs. If you calculate self-weight and live load means it's coming to downward deflection. Okay. So apply this formula minus 5/48 PEL square divided by EA. So now let us see what are the known values here. P we know. What is prestressing force? 50 kilonewton. Sorry, 200 kilonewton. Okay. And E is equal to 50 mm. And L is equal to 9 meter. And E, what is E? So E value, Young's modulus is given. What is that? 35. Okay, E value is 35 kilonewton per mm square. And I value only we don't know. So based on the formula BD cube by 12, moment of inertia, BD cube by 12, we can easily calculate the I value. So I value is equal to BD cube by 12. That means 250 into 500 cube divided by 12, which is equal to 2.6 into 10 power 9 mm power 4. Okay. So next, deflection, final deflection. So substitute in this formula, I value in this formula. So minus 5/48 into P value 200 and E value 35. That means capital E. Okay. And E value small e, eccentricity 50. So here I converted all the values in terms of mm. We know that deflection unit is mm. Okay, deflection unit is mm. So I converted all the values in terms of mm. So 9 meter I converted into mm means 9,000. Okay. Next I value also 2.6 into 10 power 9 mm power 4. And you can see E value, that means Young's modulus value also they given in mm only. Okay, you can see EC is equal to 35 kilonewton per mm square. Okay, per mm square. So all the values you have to substitute in terms of mm only. Okay, so minus 5/48 into 200 divided by 35 into E 50 into 9000 square divided by I value 2.6 into 10 power 9. So finally we got the answer in terms of mm. So that means minus 0.93 mm. So this minus value indicates the upward deflection. So in the question they asked only upward deflection. They clearly mentioned upward deflection. So upward deflection, if they first read the question, first understand the question. So if only upward deflection only they asking means you don't consider self-weight lie low. Okay, only consider pre-stressing amount of pre-stressing force only. And based on the shape of the tendon, you apply the formula. Okay, students. So I will give students, I will give 1 minute time. Understand this problem. Okay, after that we will go to second problem. Okay. If you have any doubt in this problem means you can ask me. $166 message, sir, E value is 50. Yes, E value is 50 only. You can see in this picture, in this question and the picture. They clearly mentioned eccentricity is 50 mm. So in formula also mentioned 50 mm only. You can see here 50 mm. This is P. P is 200 kilonewton. And this is E 50 mm. Substitute all the values in mm. You can see here in the calculation of deflections, proper units are to be used in the above computation. The modulus of velocity is in kilonewton per mm square, span in mm, precessing force in kilonewton, moment of inertia in mm power 4. So the resulting deflection is in mm. Students, second problem, I read the question. Estimate transfer under long-term deflection for a prestressed concrete beam of size 200 mm into 400 mm. The span of the beam is 10 meters. It is prestressed by a parabolic cable with an eccentricity of 75 mm at midspan and 0 at the ends. The initial prestressing force is 600 kilonewton and there is 20% loss. The live load consists of 3 kilonewton per meter, finishes and 1 kilonewton per meter variable load. Models of velocity of concrete 35 kilonewton per mm square. Creep coefficient is 2 and density of concrete, DC is nothing but density of concrete, 25 kilonewton per meter cube. So in this question, they are asking long-term deflection. So for long-term deflection, we have the formula. So we need to calculate self-height deflection, live load deflection, deflection due to pre-stressing force. Initially, these three things. After that, we have to calculate the long-term deflection. Okay. So now you can see here, the size of the beam is 200 into 400 mm. Okay, first draw the figure. So you can see size of the beam and the span is 10 meters. The prestressed parabolic cable. So it is a parabolic cable with an eccentricity 75 mm at middle and 0 at the ends. This is also as per previous problem only. The initial prestressing force is 600 kilonewton, 20% loss. Okay, here they given live load 3 kilonewton per meter and finishes. Finishes is nothing but tiles or granite above that, above floor finish. Okay, that is called finishes, 1 kilonewton per meter. Modulus of velocity is given, creep coefficient is given, and density of concrete also given. So based on this, draw the diagram. So first we have to calculate the self-height. How to calculate self-height? So size of the beam multiplied by density. So you can see size of the beam 0.2 meter into 0.4 meter into 1 meter length. Always we have to consider 1 meter length into 25 means 22 kilonewton per meter. This is the UDL load, self-height UDL load. Next, moment of inertia equal to BDQ by 12. So B is 200 into D is 400 cube divided by 12. Okay. Next, deflection after transfer. First, we have to consider self-height. Self-height. So deflection at transfer, we calculate a self-height per meter, 2 kilonewton per meter. So this we have to convert it into kilonewton per mm. So how to convert kilonewton per meter into kilonewton per mm? So which is equal to 2 divided by 1000. Okay, 2 divided by 1000. So now it is converted into kilonewton per mm. Okay. So deflection due to self-height, since it is like a UDL load. So for UDL load, what is the deflection formula? A simply supported beam carries UDL load. What is the deflection formula? It is 5 by 384 WL power 4 divided by EA. Okay, 5 by 384 into WL power 4 divided by EA. So substitute all the values. 5 by 384 W is 2 divided by 1000 kilonewton per mm. So you can see here, this 1000 meaning is we are converting kilonewton per meter into kilonewton per mm. Into L is 10 meter. If you converted mm is 10 into 10 power 3 power 4 divided by 35 kilonewton per mm square. E value, that means Young's modulus value they given in kilonewton per mm square only. So 35. And the moment of inertia, I value, you can see here, we already calculated BD cube by 12. This also we found in mm only. So 1.07 into 10 power 9. So substitute all the values and we found it is 6.95 mm downward. So always self-height load is acting downward. Self-height deflection. Next, deflection due to prestress. So deflection due to prestress, it is the formula is depends upon the shape of the cable profile. Okay, you can see what is the shape of the cable profile. It is parabolic cable. So therefore 5 by 48 into 600 into 75 into 10,000 square divided by 35 into 1.07. That means minus 5 by 48 PEL square divided by EA. So same formula we seen previous problem also. Okay. So it is minus, so it is upward deflection. So this arrow indicates deflection direction. Downward means downward arrow. Upward deflection means upward arrow. Okay. So here prestressing force is 600 kilonewton and eccentricity. You can see here eccentricity is 75 mm. So we have to substitute eccentricity 75 mm here. Okay. So now net deflection. Deflection at transfer equal to 6.95 downward minus 12.52 upward. So final deflection is minus, so it is upward deflection only. So minus 5.57. Okay. Next, deflection at the application of finishes. So since there will be an external live load is acting 3 kilonewton per meter. So we have to calculate that deflection also. So how to calculate? So since it is acting a UDL load 3 kilonewton per meter they given. So again same formula 5 by 384. Actually this formula is applicable for both the dead load and live load. So our concept is the formula will not vary, depends upon the load. If the load is in terms of kilonewton per meter, either it may be a dead load or a live load. So always we are calculating dead load and live load in terms of kilonewton per meter only. Okay. So we have to use this formula 5 by 384 WL power 4 divided by EA. So substitute all the values. So here also 3 kilonewton per meter they given in the meter value. So I converted into mm. So 3 divided by 1000. Okay. So substitute all the values and we got deflection in downward direction. Deflection in downward direction. So the final short-term deflection equal to deflection due to self-height minus deflection due to prestress and plus deflection due to finishes. Okay. So why sir here minus? Because deflection due to prestress is minus value only. It is upward deflection. So that we have to put this minus. And deflection due to self-height and deflection due to live load is acting downward. So plus value. So the net deflection, you can see this is deflection due to self-height 6.95 mm and deflection due to prestress minus 12.52 mm and deflection due to live load, it is plus 10.43 mm. So finally we got 4.86 mm. 4.86 mm. So this is the deflection, short-term deflection. Okay. So in the question they didn't ask a short-term deflection, they asked a long-term deflection. Okay. So how to calculate long-term deflection? So for the long-term deflection, we have one formula. What is the formula? So deflection equal to, that means deflection long-term equal to deflection due to loads. Here deflection due to loads in the sense self-height and live load. Next deflection due to prestress. Only prestress. Next loss ratio into 1 plus creep quotient. Okay. Next calculate deflection due to loads. That means self-height and live load. So we already calculated the deflection due to live load and deflection due to self-height. That means 6.95. You can see here 6.95 and 10.43. So which is equal to 17.38 mm. Okay. So net deflection equal to 17.38. That means deflection due to self-weight and live load minus what is the deflection due to pre-stressing force? It is minus 12.52. Okay, so minus 12.52. What is the loss ratio? It is 0.8. Okay, so where I from where I got this 0.8, you can see in the question. So there will be a 20% loss. 20% loss. Okay, so 20% from that 100%, 20% is lost. What is the balance one? Only 80%. So that it is in terms of fraction, it is 0.8. So don't put 0.2 or don't put 20. It is wrong. It is only loss. Loss ratio is nothing but after losses, what is the balanced one? Okay, that numerical value, not percentage value. So from this, you can see it is 0.8. Okay, next 1 plus pi. So pi is nothing but creep coefficient. That creep coefficient also given in the question. You can see here creep coefficient equal to 2. Creep coefficient is equal to 2. What is by creep? It is the deflection due to sustained load. Okay, so due to the weight of the beam, it is keep on somewhat deflected without giving any additional load. The beam will deflect during long term. Okay, it is not a short term. That means 5 years, 10 years, 15 years, 20 years, like that. Okay, so that creep coefficient is 2. So substitute all the values. That means 17.38 is the deflection due to total load minus 12.52 deflection due to pre-stress multiplied by loss ratio 0.8 and pi value 2. So substitute all the value. We got long-term deflection is 22 mm. Okay, student. So a simply supported beam of 10 meter span with rectangular section 200 mm into 400 mm is prestressed by a single cable in which the total tensile force is 250 kilonewton. Okay, the center line of the cable is parallel to the axis of the beam and 75 mm above the soffit at middle third of the span and bent straight over third span. If EC is equal to 35 kilonewton per mm square, calculate the deflection due to prestress only, deflection due to prestress plus self-height, and the magnitude of the concentrated load at 1/3 span point, which would result in limiting deflection to span by 500. This is the question. Students, first you understand what is the type of the cable profile. This is the major thing in this type of deflection problem, because the deflection due to pre-stress is based on the cable profile only. Okay, so now you can see here the center line of the cable is parallel to the axis of the beam and 75 mm above the soffit at the middle third of span and bend straight over third span. So now I will show the diagram. You can see the diagram. So you can see here the beam is separated into 1/3. That means 10 by 3. So you can see total span is 10 meter, and you can see 1/3. That means so 1/3 of 10 and 1/3 of 10 and 1/3 of 10. Okay. So the middle portion 1/3 of 10 having 125 mm eccentricity. Having 125 mm eccentricity. Okay, and so in the question you can see here they mentioned 75 mm above the soffit. They didn't give eccentricity directly, they given indirectly. So what is the overall depth? 400 mm. Okay, 400 mm. What is the center? You can see here the center of the beam is 200 mm. Okay, 200 mm. So this cable is located from the bottom. It is 75 mm. That means this height is 75 mm. So now what is, this is 75 mm. Now tell me what is eccentricity. 200 minus 75, we got 125 mm. So they given eccentricity indirectly. Okay, so soffit means bottom. The cable is located 75 mm from the soffit. That means from the bottom. So this side is this gap, cable and bottom of the beam gap is 75 mm. So from here to here 200 mm. So 200 minus 75, we got 125 mm. Okay. So under this condition, what is the deflection? We need 3 type of question answer. Okay. So due to prestress only, due to prestress plus self-height and magnitude of concentrated load at 1/3 span point, which would result in the limiting deflection to span by 500. So first thing, first we have to calculate the self-height. So they given the size of the beam. 0.2 into 0.4 into 24. The density of the concrete, normally we taken 24. It is 1. The answer is 1.92 kilonewton per meter. Next, moment of inertia, BDQ by 12. So it is 1.07 into 10 power 9 mm power 4. Next, deflection due to self-height. What is the deflection due to self-height? Since this the self-height is acting as a UDL, uniformly distributed load. So the deflection is pi by 384 into WL power 4 divided by EA. Okay, so 5 by 384 into this W value is given in kilonewton per meter. So we should convert into kilonewton per mm. So therefore 1.92 divided by 1000. Okay, so multiply by length. Length is 10 meters. So 10 into 10 power 3. That means 10,000 power 4 divided by EA. E value is given. You can see it is given in terms of mm square only. So directly put 35. So next, moment of inertia 1.07 into 10 power 9. You can see here moment of inertia. So the deflection due to self-height is 6.7 mm downward. 6.7 mm downward. This is the moment of inertia. Okay. So next, coming to deflection due to prestress. So in this deflection due to prestress, since the cable is like a trapezoidal shape, you can see here there is 2 triangle portion is there, 1 rectangle portion is there. It is like a trapezoidal. So for that we have this formula. If eccentricity is 0 at the support and eccentricity at the middle, so this is the, under this condition, deflection due to prestress, this is the formula, that is minus 0.958 into PEA square divided by EA. Okay, what is that A? So A is nothing but this 1/3 distance. You can see here, this 10 by 3 is nothing but A. This is your A. So now substitute all the values. So deflection due to prestress equal to minus 0.958 into P. P is what is the amount of prestressing force? You can see here they mentioned 250 kilonewton into E value 125. This is your E 125 mm into A square. A square is nothing but 10 by 3. So 10 we have to substitute in terms of mm. So 10,000 divided by 3 the whole square divided by EI. E is 35 and I is 1.07 into 10 power 9. Okay. So therefore it is minus 8.88 mm. 8.88 mm. Okay. So next, deflection due to prestress and self-height. Okay. So this is the answer for the first question. So what is the question? First question they ask, what is the deflection due to pre-stress? So this is the answer for the first question. Okay, answer. So minus 8.88 mm upward. This due to this pre-stress, the beam bend upwards. Next, coming to deflection due to pre-stress and self-weight. This is the answer for second question. So we already found deflection due to self-weight. How much? It is 6.7. That is the first step. Second step, in second step, we found deflection due to pre-stress. It is minus 8.88. So the summation of 6.7 minus 8.88, we got minus 2.18 mm, minus 2.18 mm upward. So here, upward deflection is more compared to self-weight deflection of the beam. So it is upward minus. So minus indicates upward deflection 2.18. So next, what is the next question they asked? What is the magnitude of concentrated load? That means, what is this W value? What is this W value? So how to find? So if in a beam two concentrated loads, equal concentrated loads are acting symmetrically, the deflection formula is 23 WL cube divided by 648 EL. This is the formula. Okay. So 23 WL cube divided by 648 EL. So it is acting downward. So plus value. Okay, students. So the magnitude of the concentrated load, which is equal to at 1/3 of the point. That means at here, and here. So the net deflection, that means deflection due to pre-stress and self-weight, minus 2.18 plus deflection due to concentrated load. That means 23 WL cube divided by 648 EL. Here W is the only unknown. We know L, we know E, and we know I, which is equal to L by 500. That means you can see here the question they given. Span by 500. The limiting deflection should be span by 500. Here span is 10,000 divided by 500. So if you equate these values, substitute L value 10,000, E value 35, and I value 1.07 into 10 power 9. Substitute all the values, we can easily got W value. Okay, this is the concentrated load, amount of concentrated load. 23.4 kilonewton is the amount of concentrated load. Okay, so for that we need all the deflection. That means deflection due to self-weight, deflection due to pre-stress, deflection due to external load. That means live load. If summation of all these three loads, okay, summation of all these three loads, which is equal to span by 500. So W is equal to 23.4 kilonewton. So in this second problem, what are the data given? A prestressed concrete beam 200 mm into 500 mm. Size of the beam is given. Next, what is the shape of the cable? It is a parabolic cable having two type of eccentricities. One is 50 mm at the end and another one is 150 mm at the midspan. And it carries a UDL load 10 kilonewton per meter. In addition to two concentrated load 10 kilonewton acting 1/4 of the span point. So that span of the beam is divided into 1/4. Okay. Next, the prestressing force is 250 kilonewton. Grade of concrete is M35. Creep coefficient is 2. Loss in prestress is 20%. So estimate the short-term and long-term deflection. Check the adequacy of the beam from the deflection criteria. Okay. Students, here you can see the span length didn't mention in the problem. Unfortunately, the span length didn't mention. Actually, it is 10 meter. Okay, it is 10 meter only. Now you can see in this diagram. So this is the diagram. So you can see here, this is the simply supported beam, 10-meter length. You can see the shape of the cable. It is parabolic cable. So at middle, the eccentricity, this eccentricity is 150 mm at middle, and at this is E1. Okay, E1, consider it is E1, and this is E2. Okay, at support, the eccentricity is 50 mm. Okay, so the UDL load is acting 10 kilonewton per meter. In addition to UDL load, 2 point loads are acting at 1/4. 1/4 means 10 by 4. It is 2.5 meter. 2.5 meter. Here 2.5 meter and here 2.5 meter. Okay, 10 kilonewton, 10 kilonewton. So this is live loads. Okay, 2 point loads and 1 UDL load is the live loads. Okay. So next, let us start the problem. As usual, first we have to start with self height. So 0.2 into 0.5 into 24. Okay, so it is 2.4 kilonewton per meter. And moment of inertia BDQ by 12. It is 2.08 into 10 power 9 mm power 4. Okay, so this is all as usual. Next, coming to deflection. So first we have to calculate deflection due to self height. So what is the self height load? Dead load, it is 2.4 divided by 1000. I converted kilonewton per mm. So 5 by 384 into 2.4 divided by 1000. Okay, so multiply by 10,000 power 4 divided by E value is 35 and I value is 2.08 into 10 power 9. So it is 4.29 mm downward. So always self height load, self height deflection, live load deflection should act acting downward only. Okay. So next, coming to live load. So live load, there are two types of loads is there. First, we have to calculate the UDL. So for UDL, what is the formula? Same formula. W 384 divided by WL power 4. Instead of W for identification, live load, they mentioned Q. Okay. So substitute the values 5 by 384 into what is the UDL load, live load? It is 10. So 10 divided by 1000. It is converted into kilonewton per mm. So multiply by 10,000 power 4 divided by E value 35 and I value 2.08 into 10 power 9. Okay, so two deflections we found. One is self height, that means dead load deflection. Second one is live load, UDL live load deflection. Next, coming to concentrated load live load deflection. So how to find? So in this book they given some complicated formula. So either you can use, otherwise you can see students, you can see here. So if 2 point loads are acting, 2 point loads are acting at a distance A, it may be 1/3 or 1/4 to 1/2, whatever may be. Okay, at distance A, this is the deflection formula. Maximum deflection. Please note down this formula. In the book, it is not available. Okay, so P into A divided by 24 EI into 3L square minus 4A square. Okay, so what is P? P is the external load, concentrated load, and A is the distance, 1/3 or 1/4. Okay, and L is the length of the span. EI is the same. So if you substitute, that means you can directly get this answer. You can see here. You directly get, you can directly get this 3.94 mm. So actually same formula only they mentioned here. Instead of they put beta, they removed PA. Okay, and everything is same. And they simplified. For same formula they simplified, but it will take confusion. So don't see this formula. Okay, don't see this and all. Okay, so this is all complicated. For easy memory purpose, you see this formula. Okay. Okay. So P into A divided by 24 EA into 3L square minus 4A square. Okay, students. If you substitute that, you can directly get the same answer. That means 3.94 downward. Okay. So we calculated self-height deflection to live load deflection. And what is the balanced one? Deflection due to pre-stress. So how to find deflection due to pre-stress? So under this condition, what is the formula? We already discussed it. So if there are two eccentricities are there, okay, in the parabolic cable, there are two eccentricities there. One is at the end, one is at the middle. Means this is the formula. PL square divided by 48 EA into minus 5 E1 plus E2. Okay. So now substitute the values. What is P? 250 kilonewton. L is 10,000. And minus 5 E1. Minus 5 E1. E1 is nothing but central deflection, 150 mm. And E2 is the end deflection at support, 50 mm. Divided by 48 into EI. E is 35 and I is 2.08 into 10 power 9. So what is the net deflection? So always this deflection is minus. Okay, so minus 5 mm upward. This is the deflection due to pre-stress. Deflection due to pre-stress. Okay, now tell me what is the short-term deflection? The summation of dead load deflection, live load deflection, and deflection due to pre-stressing force is called a short-term deflection. Okay, you sum all the values. Self-height 4.29 and live load. Two live loads are there, 17.9 plus 3.94 and deflection due to pre-stress minus 5. So the value is. So for long-term deflection, we have one formula. We already seen one formula. What is that formula? That means deflection due to all loads. This is deflection due to all loads minus delta P, deflection due to pre-stressing force, into loss ratio into 1 plus pi. What is the deflection due to all loads? Deflection due to self-height, deflection due to UDL load. Okay, this is your deflection due to self-height plus UDL load. Self-height plus live load. Next, minus. What is the deflection due to pre-stressing force? So that we already found it is minus 5 mm. Okay, substitute that minus 5 here. Deflection due to pre-stressing force. Next, loss ratio. So in this question, they given the loss percentage is 20%. Okay, so what is the remaining thing? The ratio is 1 minus 0.2. It is 0.8. 1 minus 0.2. So it is 1 minus that loss ratio, 0.2, which gives the 0.8. Okay, that means pre-stress after losses. Okay. Next, 1 plus pi. Pi is the creep coefficient. This is also given in the question too. So finally, long-term deflection is 66.4. So now you can see, students, what is the short-term deflection? 21.13 mm. But in case of long-term deflection, 66.4 mm. Okay, which one is higher? Definitely long-term deflection only higher. Next, allowable deflection. As per IS 1343 code, we already seen allowable deflection is span by 250. Span by 250. So what is our span? 10,000 divided by 250. So our span is 10,000 divided by 250. So what is the allowable limit? Okay, allowable means permissible. It should not exceed this 40 mm. So deflection should not exceed both short-term deflection as well as long-term deflection should not exceed 40 mm. The total deflection is 40 mm only. So below the 40 mm is it is good. If above the 40 mm is it is not good, the beam is not safe. So now check this 40 mm with short-term deflection and long-term deflection. you can see what is the short-term deflection. What is the short-term deflection value? 21. So it is less than 40 mm. Less than 40 mm. Is safe or not? Safe only because the deflection is less than permissible limit. Permissible deflection as per code 40 mm. Now you can see long-term deflection. Okay. So it is greater than 40 mm. It is not equal to or not less than 40 mm. It is safe or not? Not safe. Okay. So both short-term deflection and the long-term deflection should be less than 40 mm. So final result as the long-term deflection is greater than the allowable deflection. Allowable, permissible, all are same. The beam is unsafe or not safe from the deflection criteria. So what we have to do, we have to increase the depth of the beam. Automatically moment of inertia is increases, then deflection also decreases. That is the only way. Okay. So if anything, not only prestressed concrete, any beam, any material, if deflection fails, means just to increase the depth of the beam. Okay, increase the depth of the beam, automatically the deflection will get reduced. Okay, students. So any doubts, students? Ask me now.